All right, I want to come on and do a quick review of rational expressions. And so this was the concept we did in 8.2. We simplified rational expressions. So when you have a fraction like this, you cannot cancel anything that's added or subtracted. So I have 1, 2, 3, and then 4, 5 total terms in this rational expression. And unless I can take it out of all 5, I can't cancel it. So you cannot reduce the 5x's. You cannot cancel out the 1's. The only way you can cancel is by factoring. You have to have the pieces multiplied together. So we can cancel anything top to bottom as long as every piece is multiplied together. So we're looking for products. So once you factor it, we can cancel. So here's one problem showing there's nothing we can really do with this one. We could factor it and cancel, but this is not going to cancel as is. If you come down here, this is a different problem. This must have had a 5 that was a common factor, and this factored out to x plus 2, x minus 1, and you can see they have a common factor, so that we can cancel out. Okay, so it has to look like this to cancel. Then we got into, and still in 8.2, we got into multiplying and dividing. Multiplying, you want to factor as much as possible and then cancel out the common terms between any numerator and any denominator as long as it's multiplication. The big idea here is that I do not need a common denominator. Okay, we knew that. We never did common denominators with multiplying and dividing, but it starts to get confusing because we did later addition and subtraction. So with multiplying rational expressions, you're going to factor everything you can and cancel out any common factors, any top to any bottom. Okay, so cross canceling or just top to bottom. Division, we actually don't do anything with division. With division, we're going to keep the original fraction, and then we are going to flip the multiplication sign to divide, to change it from division to multiplied by the reciprocal. All right, then you go back and you do all your rules for multiplying. All right, with all of these ideas, you have to find your domain restrictions, and domain restrictions here would be the x could not be negative 1/5. We set our denominator equal to 0, and we say, well, what can't x be? So you would solve it by subtracting 1 divided by 5. Here we'd have domain restrictions. X could not be negative 2 or positive 1. So anything that has a domain restriction is because there is a variable in the denominator. All right, so then we got into what was a little bit harder, and that was 8.3, and that's addition and subtraction. And these are the ones that require a common denominator. So it does take a little bit more effort. So you need to, again, factor each piece in the denominator and build it. So that's when you need a common denominator. All right, then we have our last concept, and that was from 8.5, and that is solving rational equations. So case 1 is when you have a proportion, you can cross multiply, but I avoided that because sometimes with cross multiplication it can get a little bit sticky with higher powers and bigger numbers. So I normally look at the idea with case 2. When the original problem involves addition or subtraction, you get a common denominator first. So even when there's just two fractions equal to each other, you can still build a common denominator across the entire fraction. Okay? And I am not going to proceed with cross multiplication. I am going to get a common denominator, and I am going to set my numerators equal. So this is what it's saying. If after adding or subtracting you either have a common denominator on the left and right side of the proportion, it would be easier to get a common denominator, and you can just compare the numerators. So this is really where we're at. Okay? So looking at this, you can see that I have a common denominator. If I didn't, I would factor this, x plus 1, x minus 1. Factor x plus 1, x minus 1. If my denominators are equal, then my numerators must be equal. And so I can simply solve by taking 2x plus 3 equals 7. If I cross multiplied this, I would then have powers of x to the third and a lot more things to cancel out and factor. So much easier to get a common denominator across an equal sign, adjust your numerators if necessary, and then denominators are equal, numerators are equal. Okay, so I pulled some problems from our textbook to go over. These problems are on page 639 in the Chapter 8 Study Guide Review, and I just pulled some that I thought would be good to review with you. So let's get started. The first thing I see is just a rational expression, no addition, subtraction, multiplication, just one piece here. And so I'm looking to see the numerator isn't factor, but the denominator has a GCF, don't forget about that. And with that, I see that the 3 will reduce with the 6. And so there's not much else I can do here. I'm left with the 2x to the third over x plus 4. Not much else canceled out here. So with that in mind, we also want to talk about our domain restrictions. What can't x equal? Okay, so my denominator cannot be 0. Go back to that original denominator, but I want to look at the factored because I'm really using zero product property. 3 canceled out, but it will always be a 3. There's no variable. There's no way that could be 0, but x could be negative 4. So there is my answer. Pretty simple one, not a lot of work to do. All right, here's number 16 from the book. Again, these are just jumping around because I wanted to show which numbers they were. So now I have multiplication. I do not need a common denominator, but I do need to factor and cancel and find the pieces. So this is going to factor to x minus 2, x plus 1. We want to be very careful with our accuracy in factoring. And then up here, this factors to x, I'm going to go with plus 3 and x minus 1. Now, if you don't like to rewrite that above it, you could rewrite the whole problem. We're at the point now where I'm just not rewriting it as much. So the x plus 3's can cancel top to any bottom. The x minus 2's can cancel. And this is an x minus 1 and an x plus 1. So those are not going to cancel. So my final answer is x minus 1 over x plus 1. And let's check out our domain restrictions. And looking at my original denominators before we canceled. So here it is, I factored it. X cannot be 2 or negative 1. And here x cannot be negative 3. And there you have it. All right, number 20, we have division. We really don't do anything with division. As soon as we see a division sign, we are going to multiply by the reciprocal. So again, I don't need common denominators, and I cannot cross-cancel. I can only cross-cancel if I have multiplication. So I'm going to go ahead and sort of combine this since we've been working on it for a while. I'm going to factor and work on flipping my division problem. So I have a 3 as a GCF, x minus 7 over 3x. And then I'm going to change this to multiply by the reciprocal. So if you're doing this in one swoop, just make sure, take this piece and focus, put it on top. Okay, take out the x, x plus 7. For some people, it's better to rewrite, multiply by the reciprocal, and then come back and factor. So whatever works for you. This is now going to go to the bottom. It's a difference of squares, x plus 7, x minus 7. I've been saying this a lot. This chapter, this material really uses a lot of content that we've used this year. So it's really important that we have those to strengthen our understanding. All right, the x minus 7's will cancel. The x plus 7's will cancel. And actually, if you see it, the 3's cancel, but so do the x's. One of the common mistakes here is people say, okay, it's 0, it's all gone. The answer is 1. Remember, when 3 goes into 3, 3 goes in itself one time. X minus 7 goes in itself once, x minus 7 goes in itself once. So when we're canceling, we're really dividing it by itself. So we are left with 1, and our domain restriction comes from the original denominators. But I want to remind you, I had a denominator here, I had a denominator here, but don't forget I am dividing by this. So this also cannot be 0. Okay, so I scribbled this out a little bit too much, but x cannot be 0. This is my original numerator. Dividing by 0 doesn't work. So x cannot be a negative or a positive 7, right here. And then this was my original denominator. X cannot be 0. We have it. X cannot be negative 7. We have it. So that is our final answer. All right, so those were problems from our 8.2 content. Simplifying rational expressions, multiplying, and dividing. Then we got into 8.3, and so here's number 24. In order to add or subtract, this is the big deal. In order to add or subtract, you have to have a common denominator. All right, I did not need a common denominator. However, you cannot cross-cancel, okay? You cannot cross-cancel with addition and subtraction. And these rules get very confusing, especially when you're trying to take a quiz or a test and you're stressed out and things start getting mixed up easily. All right, so just like what we did, we want to factor, because we are not trying to factor to cancel right now. We're trying to factor to build our pieces. So this is going to factor as a perfect square, x plus 2, x minus 2. Perfect. Now, if you look at this, this has the x minus 2, same thing as this one. However, I need an x plus 2, so I'm going to build that. X plus 2, x plus 2. So there we go. Now, if you're welcome to rewrite each of these pieces, but I'm going to go ahead and funnel it down. I have that common denominator of x plus 2, x minus 2. And in my numerator, on this side I have x. I'm going to put a big plus sign over here. And on this side I have x plus 2. Alright, so I end up with having a 2x plus 2 on the top. And in the bottom, I'm going to go ahead and leave it factored. Some of you might already be looking ahead. This is what I get on the top. And on the bottom, this is how it is. So if I factor it, this would factor as a 2 and then an x plus 1. That does not have anything that cancels with my denominator. So nothing's going to reduce. So I would leave my top as 2x plus 2, and then I would FOIL the bottom, and you're going to get x squared, negative 2x, positive 2x, so 0x, minus 4. That's that difference of squares. All right, let's talk about a domain restriction. What can't x equal? Go back to the original denominators. Nothing was canceled, but let's go back up here to the originals. X cannot be negative 2 or positive 2, and then that repeats with the 2. Okay, one other thing I want to bring up is some answer keys, some textbooks do not show this answer. Sometimes they show the answer in its factored form. I like that in the way that it shows you the pieces, because if you mess up one piece, your final answer will look very different. However, to be proper, this is the final answer. You multiply it back out. All right, number 30, same idea. First thing I want to take care of, and we've been talking about this all year, let's change that sign. Now on this problem, I'm just going to do addition of the opposite, and if there was more than one thing, I would distribute it to everything in the numerator. However, if there was some time that I needed to change the denominator, I could distribute it to the denominator, so one or the other. By taking this and distributing it now, I'm not going to forget it. I'm trying to make that look a little more red. Okay, so I need to find the pieces. So we need to break this down, just like Legos. To rebuild something, you break down the original. So break this down, x minus 3, x plus 2. All right, so good news, they both have the factor of x plus 2. That's why we want to find the pieces so we don't make it bigger than it needs to be. Multiply the bottom and the top by the x minus 3 that it needs. And so then we have this common denominator of x minus 3, x plus 2. All right, so here's what I want to remind you of. I bring down my 1. Nothing had to change over here. But over here, I did have to put this here, so I'm going to distribute. If I didn't put that negative sign on the x, I'm likely to have had a negative x squared and then messed up and not change the sign. That's why I want to change that. So this would be a negative x squared and now a positive 3x. Okay, so now that I have that, I'm going to go ahead and rearrange it. Negative x squared plus 3x plus 1. Now I'm looking at this numerator, and if I wanted to, let me jump over here. I could factor out that negative 1, because I've always said factor out the negative to make it easier for our brains. And so I'm left with x squared minus 3x minus 1. This does not factor, okay? There's no factors in negative 1 to add up to negative 3. There's a coefficient of 1 up here. So that doesn't factor. So I'm going to go ahead and let that sit. And then I'm going to refoil this. But if you remember, this denominator came right from here. So since I had these pieces that came from here, you can either refoil it, but know that you're really using that original. So that is your answer. And again, let's talk about those domain restrictions. X cannot equal, okay, go back to the original here. X cannot be 3, negative 2, and a repeat of negative 2. So 3 or negative 2. All right, I have 2 more problems here. So moving right along. Looking at this problem, this is called a complex rational expression, and the reason being is you have fractions in the numerator. So if I can take you back real quick to number 20. Number 20 had a division symbol here. Notice we had a fraction, singular, divided by a fraction, and we simply multiplied by the reciprocal and followed all those rules. Now, if you take a look at this one, I have fractions divided by a fraction. So I would change this to multiply by the reciprocal, but I can't do that until I get this into a single fraction. So remember, anytime you're looking at this, you want to think about it. The top is one problem, the bottom is one problem, and then we'll come back and divide. So I need to get a common denominator here, and I don't think that's a bad problem to work with. So this sometimes is easier than some of the other addition subtraction problems. So if this has an x, this needs an x, and even though there was an x there, I need my own. And this has a 4, so this is going to need a 4. So right now I have x squared minus 4 in my top, and I have a 4x in the denominator. And be really careful, x squared minus 4, okay? The bottom is just 4x. And then since this already was a single fraction, I can just rewrite it. And now I'm back to taking my division symbol, right? This is division, division, and multiplying by the reciprocal. So I'm going to factor x plus 2, x minus 2, and then I have a denominator of 4x, and then I'm going to multiply by the reciprocal, which is x minus 2 over x plus 2. Okay, so the x plus 2's cancel, and one of the things you have to be careful about, sometimes we see these are the same, we want to cancel them. These do not cancel, they're both in the top. Okay, so we have left in our problem x minus 2 times x minus 2 all over 4x. So you might see in your textbook x minus 2 quantity squared over 4x. That is correct, but that's not the form I'm looking for. I'm looking for you to FOIL this out. This is a perfect square, so x squared, so square the first, square the last, and double the product. So x squared, we negative 2x is negative 4x, and last negative times the negatives are positive 4, all over 4x. And as easy as it is to get to the end and then make a mistake, we want to be really careful that we don't do that. I cannot take a 4 or an x out. I can take it from here and here, but I can't take the x from here, and I can't take the 4 from here. So not all of the terms have something in common. So that's my final answer. Again, that pesky domain restriction, which comes into play later. We want to look at our denominators. So we do have to be careful. There can be some different things that happen here, but our basic domain restriction, x cannot be 0, okay? And then x cannot be negative 2 or positive 2. These can get a little more complex because of the addition and subtraction, so we do have to watch sometimes what we have. All right, one more problem, and it gets into section 8.5, and 8.5 was solving rational equations. So I have two things I always think about. Thing one, if you want to quote Dr. Seuss, thing one is, do I have a common denominator? Okay, if I don't have a common denominator, I want to build one. So do I have a common denominator? And don't forget to adjust numerator and denominator. That's the first thing. All right. The second thing I want to ask myself is, do I have an equal sign? Because if I have a common denominator across everything, okay, do I have a common denominator for everything? Guess I should get more specific. Do I have a common denominator for everything? And then do I have an equal sign? And if so, then I can set my numerators and compare them. So let me do a real quick over here. Remember, this is reviewing. If I have a over b equals c over b, if I have the same denominator, then I can set my numerators equal to each other. If my denominators are equal, then my numerators are equal. So if this is true, then a must equal c. All right, so I am really treating this like addition and subtraction. So if I was ignoring the equal sign, I would put a 2 over here, and I would put an x plus 4 here. And then I could add these, get a common denominator, put them together, add up the tops, and then I could cross multiply. And I don't want to do that because that's a mess. What I'm going to do over here is I'm going to see, does anything factor? A 2 and an x plus 4. That's actually perfect. Now, some of you are catching that this 2 can cancel. And that's great, but if I reduce that 2 and cancel it, I still have a 2 here that I have to build back. So what I want to look at is, I didn't have to change this side, but I had to adjust both of these. So do I have a common denominator for everything? 2x plus 4. Okay, perfect. Common denominator. If I change the bottom, did I adjust the top? 2 Okay, perfect. Didn't change anything. Now, again, I would be skipping this step, but if you wanted to see it, what I really have here is 2x plus x squared plus 4x is equal to 2x over 2 times x plus 4. So again, this is a step I would completely skip, but I just wanted to show you as a quick reminder. If I was just doing this, I would add these two and I would get to here, I would clean it up, factor, and cancel. But I have an equal sign. So what I want to show you is if my denominators are equal, then my numerators are equal. So I am going to simply have 2x plus x squared plus 4x equals 2x. So I would have gone right from here and I would have jumped right to here. I just wanted to show you that common denominator and why it works. It's just like this. Again, if I cross multiply, I'm going to get higher powers on x. And I didn't want to have to factor those out and divide. Okay, so here's what I have. I've got a quadratic, so let me clean it up. I've got x squared. I'm going to subtract the 2x. Oh, okay, so that's going to cancel. So I have x squared plus 4x equals 0. And a lot of people get stuck right here, but I know that you can do this. Just take a minute and think about your basic GCF. That's the easy factoring that sometimes we forget because we're so overwhelmed. So I'm actually setting this equal to 0. I'm not doing a domain restriction. I'm actually solving this. And I'm going to get two answers. X is equal to 0 or x is equal to -4. Looks good. Why do we focus so much on domain restrictions? Well, for this type of reason, as well as how it affects our graphs. My domain restriction, if I go back to the original problem, because remember, we didn't cancel out our denominator, but we basically based everything on the numerator because these would have canceled themselves out eventually. I can only get rid of a common denominator if I have an equal sign. But going back to the original denominators, none of these could equal 0. Okay, well 2 is never going to equal 0. But if x was -4, that would cause a problem. So that throws out one of my answers. And so out of my two answers, x equals 0 is the only valid answer. This is an extraneous or false solution. Erroneous, any of those words work. This is an extraneous solution. And the reason it comes into play is we did not take our denominators into account. We focused on the numerators. And by doing that, if I took my 0 and put it back to the original, it will work. But if I take my -4 and I put it back into the original, I have a domain error. I cannot divide by 0. So those are a couple problems to help you review and keep working and keep practicing, especially when the problems are mixed. We want to make sure that we separate our rules. I am going to quickly show this one more time, and you can pause it if you want to, but here are those rules that I showed at the beginning. And then again, remember, we really didn't use the idea in case 1 and case 2. We really focused on this at the bottom, where if you have a common denominator and an equal sign, you can simply solve by setting and comparing the numerators. So we focused on this.